So welcome back to Math 210, Calculus 1. And today, I think we are at the end. I think we've just got one more section that we want to cover on the substitution method. In your Calculus 2 class, if you take it at Simon's Rock, will actually begin with the substitution method usually. So there should be some overlap there as I understand it. But this will pretty much conclude the course. So you should think of Calculus 1 and Calculus 2 as kind of like the same course, just like split up between 2 semesters. So Calc 2 does continue the thread pretty closely. And so what thread are we working on, generically speaking? We are working on, now that we know we can use the fundamental theorem of calculus to evaluate integrals, our next task is to develop more methods to evaluate as many integrals as we can. And then we will start doing more applications of integration. And there are two sort of main methods that you use to evaluate integrals. One of them is called the substitution method that we'll learn today. One of them is called integration by parts, which you will learn if you take Calculus 2. So if you want to evaluate a definite integral, what you need is an antiderivative. So you're kind of reversing the process of differentiation. So it turns out that all of our derivative rules will lead to corresponding integration rules. So for instance, for differentiation, we have the chain rule. And that chain rule does induce or lead to a rule for calculating integrals. And that rule is called the substitution rule. So I'll go back and remind you first about what is the chain rule. So the chain rule says that if you have a composition of two functions, like f composed with g, if you want to take the derivative of this, then this is going to be f prime, plug in g, and multiply by g prime. That's like a, I guess, written in this prime notation, that's what it looks like. But we could also use this Leibniz notation. Say like y equals g of x, and then f of g of x would just be f of y, and the prime would be take the derivative with respect to x. So you want to take the derivative with respect to x of f of y, that's going to be df dy times dy dx. So df dy is just take the derivative of f with respect to the variable y. So that's just f prime, and then you're plugging in y, of course. And then g prime is just the same thing as dy dx. So that's the chain rule. And if you use something like, oh, I don't know, like maybe, let's say f of x equals sine of x, and let's take y is equal to x squared, then you would know that sine of x squared, take the derivative, is equal to 2x times cosine of x squared. So applying that chain rule says derivative of sine is cosine, plug in your x squared, then multiply by derivative of the outside function. So let's review the chain rule. And so what if you were going backwards? So what if you started with 2x times cosine of x squared, and you wanted to integrate that? So you wanted to find an antiderivative. Well, you know that from what's written here, you know that the answer is sine of x squared plus c. But you're not always going to be given a problem where all of this is already worked out in advance. Like you might have just been given this. And then your question is, how can I calculate the antiderivative in a systematic way? Well, what I'll notice is that I've written y equals x squared. So let's probe into that a little bit. So sine of x squared, this is really sine of y. So this right-hand side is sine of y. And sine of y is the antiderivative of cosine of y dy, right? And you start to say, well, you've got sine of y plus a constant. It's the antiderivative of cosine y dy. It's also the antiderivative of 2x times cosine of x squared dx. So those two antiderivatives are equal. I mean, they could differ by a constant, but that's always true of any two antiderivatives. So these two antiderivatives are equal to each other. And so let's search for a way to make that kind of make sense and find a general rule for us. So I'll notice that, well, y is equal to x squared. So cosine x squared is equal to cosine y. So this makes sense. That this is the substitution part of the substitution rule. You're kind of substituting y for x squared. So what's left over? What's left over is 2x dx and dy. And what I'll kind of remark about that, and this is the reason why we use this notation for antiderivatives, but the thing I'll remark about that is if y is equal to x squared, dy over dx is equal to 2x. And even if you know that dy dx is not literally a fraction, it's a limit of fractions, it's a limit of difference quotients. But for the purposes of this formula, it doesn't hurt you if you treat it as a fraction. So you can think dy equals 2x dx. Think of yourself as like multiplying by dx and getting dy equals 2x dx. I'll explain more about that in a second. And if you think that way, what you see here is like if you rewrite this as cosine x squared times 2x dx, then this part will become dy, and this part will become cosine y. And you'll see it's just equal to cosine y dy. And this thing you can quickly find an antiderivative of. You know the antiderivative of cosine is sine y plus c. And then to convert it back into variable x, you would just say sine of x squared plus c. So what I'm landing on is what we call the substitution rule. So if you're, and I'll do it again from the beginning. So if you're given a problem like this, 2x cosine x squared dx, and you want to integrate this, you might try making a substitution, and you're saying, well, I'm seeing that x squared, so what if I just make the substitution that y is equal to x squared? And therefore dy dx is 2x, or in other words, dy equals 2x dx. So in general, if y is equal to f of x, you might write dy equals f prime of x dx. And then you say, oh, wow, so 2x dx also appears here. So I can just literally make the substitutions y for x squared and dy for 2x dx. And that'll take care of the chain rule for me. And I'll be left with integral of cosine y. dy equals sine y plus c, which you'll then convert back to sine x squared plus c for your final answer. So the idea is in the same way that if you want to differentiate a composition, you have to include this extra term of y prime. If you want to integrate a substitution, you will also have to look for an extra factor of the derivative. And you can keep track of that by just noting that the derivative of your substitution is whatever it is, and then just, put your variable dx there. And so that keeps track of it. And so this is called the substitution rule. It's a really useful tool for calculating integrals. And I want to explain and kind of defend this notation a little bit more. If you remember back to our discussion of chapter 4, so we were doing linear approximation. So we noticed that if y is equal to f of x, then a change in y is roughly equal, like a small change in y is roughly going to be not equal to a small change in x. It would actually be equal to the derivative times a small change in x. That's what, that's what calculus is. It's telling you that the slope of the tangent line is equal to the derivative at that point. And delta y over delta x, of course, is the slope of a secant line. So if you take a small change, meaning the secant line is kind of close to the tangent line, then delta y over delta x will be roughly equal to f prime. Or in other words, if you want to estimate a small change in f, you can calculate the derivative at a point and multiply it by a small change in y. What we're thinking of here is changing the variable from x to y. So you've got a variable y related to variable x by y equals x squared. And therefore, a small change in variable y would have to correspond to a small change in variable x times that derivative. The problem with that, well, there's no problem with this formula, but the issue in using it in actual calculations is this squiggly equal sign. But actually, as you take the limit as delta x goes to 0, that squiggly equal becomes literally equal. And we denote that process of taking a limit by writing that dy is literally equal to f prime of x times dx. So these two formulas are basically the same, but we introduce dy dy and dx, excuse me, we introduce dy and dx to say that in the limit, that ratio literally becomes f prime of x, not just partly equal to. So this expression here is really phrased correctly. You know, there's nothing really wrong with it. And then when you go into higher mathematics, you'll find other ways of interpreting it in like a rigorous context. But for calculus, the notation for indefinite integrals that we have invented was specially designed so that you could make these substitutions and it would work out with the chain rule. Like when you're changing from variable x to variable y, you don't just get to do that with no with no other substitution. When you change from variable x to variable y, you have to respect the fact that an infinitesimal change in variable y actually corresponds to an infinitesimal change in variable x times the derivative. So that's where that is coming from. It takes a while to get used to, but it's really slick, well-designed notation. So are there any questions or comments about anything that I'm saying so far? Okay. So I'll sum this up. So this is the rule that appears in the textbook, and they like to use u instead of y. So they'll use u of x. Well, they'll just like to use u of x instead of y. So they'll write du equals u prime of x times dx. So you should think about this as you've got one variable x and another variable u that you can write in terms of x. And so small change in u is u prime times dx. And then the substitution rule says that if you want to take the integral of f of u of x times u prime of x dx, then this is actually equal to. See, this is why I don't like to use u as much, because then you have to say like fu all the time, but you know, f of u. But whatever. So, and then if you can find an antiderivative of this, then that's what the answer will be. So with f prime of u equals f of u. And so that's kind of like, in some sense, that's like abstract mumbo jumbo, but it's just a formula keeping track of what I showed you in that example, where you've got a composition multiplied by its derivative, and you can kind of invert the chain rule. Thanks. You can kind of invert the chain rule by saying that this is really integral of just that outside function, but then you have to make sure and redo that substitution. So eventually you'll actually plug in the u of x plus c. So you're going to get nice and comfy with this by doing a bunch of examples. And let's see some of them. So let's take, I've given you one example, but let's take some more. So now I'll switch from trying to justify the substitution rule and switch towards like showing you how to use it in practice. So like here's some examples from the book basically. So take integral of x times x squared. plus 9 raised to the 5th power dx. This example is basically an old joke because at end of semester exams, the professor typically puts an example like this where you might be tempted to multiply this out. And if you do have the fortitude to do that, I mean, you can multiply x to the 5th, x squared plus 9 to the 5th. You can use something called the binomial formula to do that and multiply x and then integrate term by term. You're allowed to do that, but that's like, if you do that, that's like, that's like one of those clown TikToks. Because there's a much simpler way to do this, which is to make a substitution, to make, say, u equal to x squared plus 9. And the reason why you might think you can do this is because you've got an x here, and the derivative of u would be 2x. It's not quite the same, but close. But if you can pull off this substitution, it'll be really much easier to do. So let's check it out. So u is x squared plus 9, and then du would be 2x times dx, excuse me. So reflecting the fact that du over dx is equal to 2x. And so let's do this substitution. So this is going to be integral of u to the 5th, that's a lot nicer. And then what's left is x dx. And you'll notice that that's not exactly equal to du, because du would be 2x times dx. But what you can do instead is just like this one simple trick. So divide both sides by 1/2. And then you're good. So a small change in u would correspond to 2x times dx, but 1/2 of a small change in u would correspond to x times dx. So that makes sense. And so therefore x dx is equal to 1/2 times du. So you can rewrite this as just 1/2 times u to the 5th times du. And now this you can integrate really straightforwardly. So this is 1/2 times the integral of u to the 5th is u to the 6th over 6 plus a constant. So 2 times 6 is 12, so 1/12. And back substitute, so u was equal to x squared plus 9 plus a constant. And so here you've to the 6th. And so here now you've cleanly done this integral. Any derivative of x times x squared plus 9 to the 5th is equal to 1/12 x squared plus 9 to the 6th plus a constant. Which makes perfect sense if you think about it, because when you take the derivative of this, the 6 will come down, and you'll be left with 1/2 x squared plus 9 to the 5th. And then when you take the derivative of the inside function, you'll get an extra factor of 2, which will cancel the 1/2, and you'll just be left with x times x squared plus 9 to the 5th. So you can see how this rule is specially designed to give you any derivatives such that when you take the derivative, the chain rule applies and then gives you back exactly what you started with. Are there any questions or comments on any of that? Okay, let's do more problems. I'll run through some more examples and then I'll give you time and space to do some problems too. So let's integrate sine of 7 theta plus 5. D theta. And so what u substitution can we use? Let's take u equal to 7 theta plus 5, and then du would be equal to 7 d theta. So the derivative with respect to theta is equal to 7. And therefore, d theta would be 1/7 of du. So plugging everything in, you'll get the integral of sine u du divided by 7. So you see what I'm doing? I'm substituting 7 theta plus 5 for u, and I'm substituting d theta for 1/7 times du. And I like to put the constants outside of the integral. And so this is 1/7. The integral of sine, or the antiderivative of sine, is what? Negative cosine. And then plus an arbitrary constant. And finally, I should rewrite my answer in terms of theta, so I should back substitute 1/7 cosine 7 theta plus 5 plus c. And by the way, so I've been talking about how to do indefinite integrals, but what about definite integrals? And so what about a definite integral? So like, actually, let's just do this one. But what if I had some bounds on it? Like, what if I were doing integral from maybe 9 to actually, I'll just do 0 to 1. Let's keep it simple. What if I were doing integral from 0 to 1 of x times x squared plus 9 to the 5th dx? So I still want to choose u equals x squared plus 9, and I still want to notice that du is 2x dx, and therefore 1/2 du is x dx. But the difference is when you use, so when you do a definite integral, like how do you do it? You take an antiderivative and evaluate it from x goes from 0 to x goes to 1. And so the whole point of doing this is that you find an antiderivative. So you would evaluate this from x goes to 0 to x goes to 1. On the other hand, if I back up a couple steps, this is an antiderivative, right? It's just written in terms of variable u. So what if I just did my substitution rule? I got the answer 1/2 integral of u to the 5th du. This is my antiderivative, and I would need to integrate this or evaluate this at the endpoints from x equal to 0 to x equal to 1, right? Because my bounds of integration are written in x. And I stress to you that that's literally what the fundamental theorem of calculus says, which is if you find an antiderivative, you can evaluate it at those two endpoints. And instead of skipping to the end, I wrote it like this because I want to show you something that's like a general principle. But there is a mismatch here because you have everything written in terms of u, whereas your bounds are written in terms of x. So how would you like account for that? Well, if x, you account for it with this formula. So if x is equal to 0, what is u going to be equal to? It would be equal to 9. So if I, basically what I'm saying is if I want to convert these x values into u values, that's going to be u of 0, and then x equal to 1 would be u of 1. So I've got an antiderivative written in terms of u, and therefore I've got my antiderivative written in u, and I've got my bounds written in u. And there's another way to write this that's like more simple, I guess. You could just write 1/2 integral from u of 0 to u of 1, u to the 5th du. Because again, what this means is take an antiderivative and evaluate it at the endpoints. And so when you do that, like, let's go ahead and do that and see what answer we get. So integral of u to the 5th is u to the 6th over 6, and like plus an arbitrary constant, but you can pick any antiderivative when you're doing fundamental theorem of calculus. So I just choose the constant to be equal to 0. And I go from u of 0 to u of 1, which is going to be 9 to 10. And I plug this in, and it's going to be 1/2 times 6, which is 1/12. So this is 10 to the 6 minus 9 to the 6th. And that is the answer to this problem. In the definite integral, the answer will definitely be a single real number. It's the signed area under the curve. For indefinite integral, the answer is going to be an antiderivative. It'll be a function. Let's compare it to what I get here, because if I did, x goes from 0 to 1. Here's my antiderivative, and let's take c equals 0. And I would be going from 0 to 1. And so like here, I've got the variable written in terms of x. So it is appropriate to go from x equals 0 to x equal to 1. And if I do that, plugging in 1 would give me, so I've got, 1/12 outside, and plugging in 1 would give me 10 to the 6, subtracting, plugging in 0 would give me 9 to the 6. So if you write out your antiderivative in terms of x, you can take x goes from 0 to 1, that's fine. If you want to write out your antiderivative in terms of u, then you would need to, again, x goes from 0 to 1, but u would go from 9 to 10. So if you want to calculate it this way, like I did here, you have to use, the variables have to match, is what I'm saying. Like if you have an antiderivative in terms of u, you write your bounds in terms of u. If you choose to unsubstitute and get your antiderivative in terms of x, then keep your bounds written in terms of x. So it has to match like that. So any questions on what I showed there? And this is completely general. So if you're doing a definite integral from a to b of f of u of x times u prime of x dx, all you have to do is find an antiderivative and evaluate that from a to b. So the antiderivative of this is f of u du, but as we discussed, the x values go from a to b, the u values go from u of a to u of b. And so this is what's called the substitution rule for definite integrals. And so that's theorem 2 on page 342, if you're tracking along with the book. And the proof of that is really just what I showed here, but just with f instead of an actual function. The proof of that is that if you want to take, this and do a substitution, then fundamental theorem of calculus says that an antiderivative for this is given by f of u du. And you would just take that antiderivative from x goes to a to x goes to b. And when you plug that in, you'll get, u of a, like f of u of b minus f of u of a, which is the same thing as just taking a definite integral from u of a to u of b of f of u du. Again, justifying this notation for the indefinite integral, because you make a definite integral by using an antiderivative and evaluating it at the endpoints. This antiderivative is written in u, so we can rewrite our endpoints in terms of u, and we're finished. Okay. So more examples. This stuff is less about memorizing theorems and more about learning how to use the rule in practice. So let's take this integral from 1 to 3 of x over x squared plus 1 dx. So this is pretty typical of a problem that you might see. And it also shows you how easy it is, I think, to get to struggle with this, because you might look at this and not know what to do. The first thing that you have to do, or the thing that you have to get used to, is how do I choose a substitution? And it's not always so easy, but in this case, I am always keeping my eye out for a function whose derivative appears somewhere. And if I take the derivative of x squared plus 1, that gives me 2x, and up to a constant that's equal to x. So that's kind of a natural choice. So if I take u equals x squared plus 1, then du equals 2x, and therefore x dx would be 1/2 du. So I can just perform my substitutions. X went from 1 to 3, so u will go from 2, plugging in x equals 1, to 10, plugging in x equal to 3. And 1 over x squared plus 1 becomes 1 over u. And x dx becomes 1/2 du. And so this is great. So you can integrate 1 over u as long as x is as long as u is always bigger than 0, or u is always less than 0. If you cross u equals 0, you run into a problem with a singularity there. But going from 2 to 10, so that's good. And so I'll just get 1/2, and then the integral of this is, or the antiderivative is natural log absolute value of u from 2 to 10, which is now 1/2 natural log of 10 minus natural log of 2. And if you want to be a little fancy, what is it? The difference of those logs would be 1/2 natural log of 5. I remember my logarithm rules right, and so this would actually be now natural log of the square root of 5 using the other logarithm rule. And this was a book example, so I can even like check myself. Yeah, they didn't reduce it, but whatever. That is kind of a nice answer to the question. So any questions or comments on that? We'll show you just one more before showing you practice problems. Let's check out the integral from 0 to pi over 4 of tangent cubed theta times secant squared theta. So integral from 0 to pi over 4 of tangent cubed theta times secant squared theta. And at first, this might look kind of difficult, but you have to think, where is a natural substitution and what's the derivative? So you have to remember your derivatives of trig functions. Like natural choices for u are going to be either tangent theta or secant theta. If I try u equals tangent theta, then du would be derivative of tangent is secant squared theta d theta. And that's, okay, well, that kind of makes me realize that this was a great choice for a substitution. Because I can rewrite this now. It's integral from tangent of 0 to tangent of pi over 4. And so tangent cubed, that's u cubed. Secant squared theta d theta is du. So this is u to the 4th over 4. Tangent 0 is 0, and tangent pi over 4 is equal to 1. And to answer your question, yes, yes, we do want to know values of trig functions at these basic radian angles, like 0, pi over 6, pi over 3, pi over 4. Make sure you can either memorize those or figure them out. And so here we're going from 0 to 1 then. So I just take plugging in 1, I get 1/4, and plugging in 0, I get 0. So this is telling me that the signed area under the curve of tangent cubed times secant squared is actually just equal to 1/4. So you can see that was a little bit of a contrived problem because everything worked out really, really well. If you go to the exercises in section 5.7, you'll see about almost 80 computational exercises. So you kind of just grind through them. So let's start you out on a couple. Just pick some of these at random. Let's start out with number 10. The instructions are find the antiderivative. It's 8 minus x to 2/3 dx. And they give you the substitution to make. They tell you to substitute u equal to 8 minus x. So take 1 minute, please do that problem. After giving you almost a minute, u is given to us. What's du? just be the negative of dx. So in other words, a small change forward in the variable u would be the same as a small change backwards in the variable x because of that presence of that negative sign. So we go through and substitute and do the rule. So this is equal to u to the 2/3 and dx becomes negative du. I always like to put the constant outside the integral. And here we're just using now the basically the power rule, but for integrals. So this is negative u to the 2/3 plus 1, that's 5/3, over 5/3, which is like multiplying by 3/5, plus c. And then to rewrite it back in terms of x, it's minus 3/5, 8 minus x to the 5/3 plus c. You can check your answer by differentiating this. Differentiate it, comes down the 5/3, cancels with the 3/5. Then multiplying by the derivative of the inside function brings out that negative sign, cancels it. You get exactly 8 minus x to the 2/3. That was question number 8. If you're following along, let's look at question number 75. Let's go all the way to the other end and see what kinds of questions they're asking you after you've done 74 others. So let's take integral of tangent of natural log of x divided by x dx. And this time the substitution is not given to you. So what do you do when you see this integral on an exam? Take a minute and work it out. So after giving you a minute, there's a substitution crying out for us, and that's this inside the parentheses thing. So let's take u equal to natural log of x. Du, well, the derivative of natural log is 1 over x dx. It's quite lovely. I'm seeing 1 over x times dx there. So this is going to evaluate to tangent of u times du. What's the antiderivative of tangent? Does anybody remember that? Have we seen that? What's the antiderivative of tangent? The derivative of tangent is secant squared. So the antiderivative of secant squared is equal to tangent. Is this like secant tangent? Okay, yeah. How do we solve this? I don't think this is a well-known formula that you'll just like immediately know. So whenever that happens, let's just try to investigate, like, what is this? This is sine u over cosine u du. Yeah, so this problem was a little bit more difficult than I expected at the beginning, because we did this substitution, we got that the answer was integral of tangent, but then I realized I didn't know what is the antiderivative of tangent. If you knew, then you had solved the problem immediately, but I do not know. So I need to do more work. So I realized tangent was sine over cosine. And I'm not sure what this antiderivative is, but I do think that I might be able to do another substitution, because the derivative of cosine is negative sine. So here's my idea. Like if I do a new substitution, like why not change variables again? Why not take w equals cosine of u? So dw equals minus sine of u du. And then I'm going to go in here again. So I'm going to say sine of u du, I see that here, is equal to minus dw, so negative sine. And 1 over cosine becomes 1 over w. So when you get more practice doing this, you'll start to see these. It seems kind of wild when you first see it, but these are common substitutions. And this I can actually integrate, because I can integrate 1 over w. I remember that's the natural log of the absolute value of w plus c. And so now I unsubstitute and say w was cosine of u. So this is equal to negative natural log of cosine of u plus a constant. I'm not quite done yet, because actually u was equal to natural log of x, and this problem was presented to me in terms of x. So I should write the answer in terms of x. So that's minus natural log absolute value of cosine of natural log of x plus a constant. So yeah, I wasn't going to be figuring out this one just from nothing in my head. I think we had to go back. So this was question 75, so it's a little further down in the book, a little bit more challenging. That's fine. And the trick to doing that was making one substitution that kind of popped out at us, getting to this point, struggling a little bit, rewriting what is tangent, sine over cosine, stare at this and realize that I can do another substitution to transform this into like 1 over w, and I get that sine u du becoming negative dw. That gives me negative natural log of w plus constant. W is cosine u, but u is natural log of x. So finally, it's natural log cosine natural log plus constant. So that's pretty cool. It's like a fun little game you can play with using that substitution rule. So for me, I think that's all I really want to say to you about calculus. Maybe 30 or so hours of talking and chatting and doing problems. So that gives us one more class period on, I have 2 more class periods, because we have one more class period on Monday, one more on Wednesday, and then we'll have the final exam on Friday. So that's going to give us 2 days to do a semester review and tend towards any questions, anything you want to talk about. So no new material after this point. If you've got outstanding things you need to turn in, you can turn them in, work on them, bring your questions to class. Let's use those final 2 hours to workshop any questions you've got and get prepared for that final exam. We'll also do course evaluations next week. I'm required to give you time to do them in class, but I'll also put a link up that you can fill out anytime you want. Do like to see 100% participation with those course evaluations whenever possible. So look for that coming up next week. So thank you everybody for your time and attention. It's been a wonderful semester, and keep in touch with any questions, comments. Take care.